Welcome back. In this video, I'm going to show you how do we derive a formula for Wronskian for a second order differential equation. So you have a second order differential equation in the standard form. So the coefficient of y double prime is 1, and then the coefficient of y prime is px, which is a function of x only. Coefficient of y is q, which is also a function of x only. Then you can look at the coefficient of first derivative and then find the Wronskian, which is c is a constant times e to the power minus integral of p with respect to x. Okay, so the purpose here is to find this formula. So we're going to start with two solutions, y1 and y2. So that means y1 and y2 both satisfy your differential equation. So you replace y with y1 and y with y2 in order to ensure that both satisfy the differential equation. Okay, so then you're going to derive a differential equation for Wronskian, and to do that you can see that the equation 1 and 2 you can definitely multiply equation 1 by negative y2 and equation 2 by equation 1 by negative y2, and equation 2 if you multiply with negative with positive y1 and then add them together. So let's see what happens. So take equation 1, multiply with negative y2, so negative y2 y1 double prime minus p y1 prime negative y2 minus q y1 negative y2. Now take equation 2 and multiply this with positive y1, so y1 times y2 double prime plus p y prime 2 multiplied with y1 plus q y2 multiplied with y1 equals 0. So then once you have multiplied equation 1 with negative y2 and equation 2 with negative y1, you can add them together, and if you add, you can see that the last term get cancelled. So you have y1 y2 double prime minus y2 y1 double prime, okay, plus p times y2 prime y1 minus y1 prime y2 equals 0. So what you do next, you look at this new equation and try to relate this equation with the Wronskian. So let's call this new equation by a number, so equation number 3, and now you calculate the Wronskian. So by definition, Wronskian of two functions y1 and y2 is just this determinant. So in the determinant, first row you write the functions, and in the second row you write the derivative of the functions, and then you do the cross multiplication, y prime 2 y1 minus y prime 1 y2, and you see that in equation number 3 in the last term p times the Wronskian w, so you can replace the last term with w. Now what happens to the first term? To derive that, you first calculate the derivative of Wronskian. So differentiate. So this is a derivative of the first term and derivative of the second term. So to be clear, I'm just going to write one more step. Y, so y prime 2 times y1. So you differentiate these. So it's a product rule. Y double prime 2 y1 plus y prime 2 y prime 1. So first function, second function, minus, again this is a product rule, but because of the minus sign you start with an opening bracket. So first function y double prime 1 y2 and plus y prime 1 is just my first function and y prime 2 is the second function differentiated. And you can see that this term here and this term there, those two terms get cancelled out. Y double prime 2 y1 minus y prime 1 y double prime 1 y2, and you see that what I have for w prime, this is the first term in equation 3. So you can modify equation 3 and you get a simple, nice first order differential equation. Okay, then this is separable, or you can, this is linear equation, so you can find an integrating factor. It doesn't matter because we want to find the solution. So let's look at the separable. So we separate equals 0. Now we integrate ln of w plus integral of p dx equals a constant c1. So w equals, take the integral p to the right hand side, which will be negative, and then e to the negative p dx, and then you have e to the c1, which is a constant. You write it here, and this is your Wronskian, and we can treat this as a formula if we wish. So you can see that you have a differential equation in the standard form, which must be a second order differential equation, and if you know only the coefficient of the first derivative term, you can calculate the Wronskian, and by doing so you can figure out whether the Wronskian is 0 or not, and it does not require solving your differential equation, which is nice. Now in the next example, I'm going to talk about the interval of existence. So find the largest interval in which the initial value problem so here is the differential equation, and it has two initial conditions. It is a second order differential equation. it will have two solutions. So there are two parameters, so you need two condition as discussed earlier. So find the largest interval in which the initial value problem has a unique solution. And we are going to call this interval as interval of uniqueness. And this is something we need to understand, and it's always a good idea. Doesn't matter where you are taking a course, you will be tested for the knowledge. So it is really you have to look at how to calculate or how to figure out what is the interval of existence. And we know that in order to look for, or in order to understand the interval of existence, the first thing you write, it's a good idea to write the equation in the standard form, and that's what we need to do to properly figure out what is the interval of existence. That simplifies the use of the theorem if you write it in the standard form. So now in this standard form, it is a second order differential equation. So its coefficient a2x is 1, which is not 0, that is a requirement. Then its coefficient of first derivative a1x is 1 by x minus 3, and the coefficient of the other term, non-derivative term, is x plus 3 divided by x square minus 3x with a negative sign in front of that, and the right hand side, which is f of x, is exactly 0. So for unique solution, we know that the highest derivative coefficient cannot be 0. So we made it 1 to ensure that this is not 0, and we need to divide by that by the coefficient to ensure in the standard form. Otherwise it may be a little complicated to figure out. So now you look at each other coefficient, so you find in which interval all the coefficients are continuous, and that's the goal. So in order to find in which interval it is continuous, so you go in the reverse way, you find where it is discontinuous, where it fails to be continuous, and then you neglect the points where it fails to be continuous. Because if you look at discontinuity of a1x, so for a1x, a1x implies that x minus 3 equal to 0 is a point of discontinuity. Point of discontinuity, or where it fails to be defined, so is undefined. If x minus 3 is 0, for a0x, we see that x times x minus 3 equals 0. So which is a singular point. In other words, you can say singular point. Singular point. Okay. So then we have from the first condition, and also in the right hand side, f of x is 0, so there is no singular point, but you have to look at also the right hand side. So in this case it is simplified. So you have x equal to 0, x equal to 3, there are two singular points. So you look at the real line 0 to 3. So you have three intervals from negative infinity to 0, 0 to 3, 3 to infinity, and you want to find the largest interval where the solution is unique. And if you compare those three intervals, negative infinity to 0 is larger than 0 to 3, 0 to 3 is smaller than 3 to infinity. So negative infinity to 0 is the largest interval. Wait a minute. So this might be going to a wrong answer or right answer. So let's see what else is given. So if you go back and look at that, there are initial conditions. So it is not that only the coefficient has to be continuous. The coefficients has to be continuous, but the interval also must contain the initial condition. So the initial condition is given at x equal to 1. And now you find that first thing that you check which interval contains that x equal to 1. And you see that this is the only interval which is actually the smallest among the three intervals, which contains the initial condition. So the initial condition is contained in the smallest of the three intervals. So this smallest interval will be our largest interval. So by largest interval, we don't mean how large the interval is. We actually mean how large the interval can be made around the initial condition. So if x equal to 1, so you take the point here, x equal to 1, and then you try to expand this. If you go to the right, you can't go beyond 3 because 3 is a singular point. You can't go beyond 0 to the left because that is a singular point. So the largest interval is 0 to 3. Let's look at open interval. 0 to 3 is because 0 and 3 are not included or cannot have a continuous solution for the coefficient. So let's see if we take a second example. And this time right hand side is not 0. Okay, so you want to find the largest interval where the solution is unique. So you form the equation in the standard form. So you divide by x times x minus 4, but then x get cancelled. Now plus divide 4 by 4y by x times x minus 3, and then also 2 divided by x times x minus 4 to also get divided. Okay, so now here you can see a0 equals 1. This is a2 equals 1, a1, a0, and f. You identify them, and all we need to look at the singular points. The singular points are given by x minus 4 equals 0 for the coefficient a1, x times x minus 4 equals 0 for the coefficient a0 and 4 also for the right hand side f. So that gives me x equal to 4, x equal to 0, x equal to 4. Okay, so then I look at the real line. So I try to isolate the interval 0, 4, here is 4, and then I isolate where is my initial condition. So the initial condition is here. These two interval, doesn't matter how large they are, they do not contain my initial condition. So interval of existence and interval of existence is just 0 to 4, and there could be different way of writing it down. Different people write it in different mathematical notation. So you can say 0 less than x less than 4, so this is your interval of existence, or 0 comma 4 and use a round bracket, or you can use a set notation. D equals, start with a curly bracket, you say for all x are included in the set such that, so colon means such that 0 is less than x is less than 4. You can use this notation, or even you can say such that x belongs to 0, 4. Okay, so it does not matter which one, which notation you use. You see that the process of identifying the interval of existence is you convert the equation into the standard form. If it is not in the standard form, then all you need to do is two steps. In the first step, find the singular points, or the points where all coefficients, including right hand side, do not exist. And do not exist means those points, once you divide by the coefficient of highest derivative, then there could be the fraction, and if it is fraction, then you look at the denominator 0, set the denominator 0, then you get the singular points. And once you get the singular points, you identify the interval and isolate which interval contains the initial condition. So we normally ask you find the largest interval, but if you ignore initial condition and find the largest interval, that will be incorrect. So you have to find the interval as large as possible that contains the initial condition. So in this case here is the initial condition 3. So 1 to 3.5 or 1 to 4 also will be the interval of existence, and 0 to 4 is also the interval of existence. So the largest possible interval is from 0 to 4, and 0 and 4 are not included in the interval because they are singular points. Hope this is clear. Thank you very much for watching.